its potential energy will be decreasing. So the decrease in potential energy will change into the kinetic energy. Hello students, welcome to class 10 physics video series. In this video we are discussing chapter 1 vibration and waves. In that lesson 1 periodic motion, and in this video we will cover lesson 1 periodic motion. We will be discussing what is periodic motion, properties of periodic motion, deforming force and restoring force, simple harmonic motion, Hooke's law, potential energy of spring, energy of oscillation and energy of a simple pendulum and spring and mass. Then we will discuss about pendulum, a simple pendulum, and at last resonance. So we will start with first concept, that is periodic motion. Number 1, periodic motion. So what is periodic motion? Periodic means something repeats after equal time interval, after a fixed time interval, repeating after a fixed time interval. So the meaning of periodic is repeating after a fixed time interval, For example, every day at 7 o'clock going to school, every day at 7, so that is repeating every day, so that is periodic. So anything that repeat after a fixed time interval, that is periodic motion. Sleeping every day at 10 p.m. So if I sleep every day at 10 p.m, so that is repeating after, repeating at that 10 p.m. every day, so it is periodic. Here periodic motion means a motion that repeats, after a fixed time interval, that is periodic motion. For example, a swing in a park, like this swing. So how does it move? It moves back, then forward, then backward, forward, backward, forward, like this. So the swing is repeating its motion, after equal time interval, so that is periodic motion. Then an object, it is moving along a circular path. At a constant speed. So this object, it starts from here. This point is, I will mark A, and it complete one rotation and reaching here. For example, it complete one rotation in 5 minutes. Again it rotates, take 5 minutes. Again it rotates, takes 5 minutes. Like that, the object is repeating its motion along the circular path at a constant speed. This is an example of periodic motion. Then motion of a spring and mass. I will take a spring. Yes. Another example for periodic motion is the oscillation of a spring. This is given in your textbook as an example for periodic motion. For example, this spring. So this spring is oscillating like this. So it is repeating, this mass is repeating its motion after a fixed time interval. So this is called periodic motion. All these examples I have given are examples of periodic motion. First one, the motion of swing, an object is moving along a circular path, and oscillation of a spring. All these are examples for periodic motion. The next is, what are the properties of periodic motion? Now we will talk about properties of periodic motion. Number 1, the amplitude of the oscillation. So what is the meaning of amplitude of a periodic motion? So here the swing is here. So that is the equilibrium position, right? The swing was here, the swing was here. So that position is the equilibrium position. So I will write here, this is the equilibrium position. Then you can see when the child push the swing backwards up to here, so the swing displaced this much distance. The swing displaced this much distance. This I will mark X. The displacement of the swing, right? So the maximum displacement, now the swing is here. So this is the maximum displacement from the equilibrium position to here. From the equilibrium position to here. That is the maximum displacement. So what is amplitude? That is the amplitude. The maximum displacement is called amplitude. Amplitude is the maximum displacement of an oscillation. So maximum displacement of an oscillation is called amplitude. So for a swing, from the equilibrium position, this is the equilibrium position. From the equilibrium position, it is displaced up to here. So this is the amplitude, the maximum displacement from the equilibrium position. Equilibrium position we also call mean position. So amplitude is the maximum displacement from the equilibrium position. You can take a notebook and you first write this heading and you can start writing the definition of the amplitude. What is amplitude? Amplitude is maximum displacement from equilibrium position, that is called amplitude. So you can write it down, write this. Then we will move to the next property of the periodic motion, that is the amplitude. Then we have time period. So what is the meaning of time period? So I will erase this from here. And here amplitude that we represent by the letter A, we represent amplitude by the letter A. So amplitude is displacement. So what is the SI unit? The unit of amplitude, that is meter. Meter is the unit for amplitude because it is displacement. Note it down. Now second property is number 2. Second property, that is the time period. What's the meaning of time period of an oscillation or time period of a periodic motion? Time period means time taken to complete one full motion. Time taken to complete one full motion means time taken to complete a cycle. For this swing, time period means first it is going like this, right? Or if it is starting from here, motion starting from here, then going forward, then back to the same place, that is one cycle of motion, and the time taken to complete one cycle is called time period. For a circular motion, what is the meaning of time period? The time taken to complete one full rotation, started from this point A, moving along the circular path and reaching the point A, that is one cycle, one complete path. So the time taken to complete one full circle is called time period for a circular motion. Time period we represent by the letter T, capital letter T. So what is time period? Time period is time to complete or time taken to complete one cycle. Time taken to complete one cycle of motion means one full motion. That is called time period, and the unit of time period. So time period is time, right? What is the unit of time? Unit of time is, yes, second. S. Now the third property is frequency. What is the frequency of periodic motion? What is the frequency of a periodic motion? So here time period, so this is time period T and frequency F. Okay, so the next is frequency, the third one, frequency. So what frequency we will represent by small letter f. What is the frequency of periodic motion? Frequency means how many cycles completed in 1 second. For example, this is a small boy on a swing. So he is swinging like this, and it takes from he is starting from here. For example, it takes like this and like this, then going like this, then like this. So if it complete like 2 cycles means one full oscillation is called cycles, right? So if the child complete 2 cycles in 1 second, then 2 is the frequency. If child complete 5 oscillations, like 5 cycles of motion in 1 second, then frequency is 5. For example, this object will complete 1 full rotation in 1 second, then frequency is 1. If it complete 2 full rotation in 1 second, then frequency is 2. If it complete 10 full rotations in 1 second, frequency is 10. And if the tire of a car rotates, for example, if it rotates 20 times in 1 second, then the frequency is 20. So frequency means number of cycles completed in 1 second. Number of cycles completed per second. Number of cycles completed per second means number of cycles completed in 1 second. That is called the frequency of the periodic motion. So what is the unit for frequency? The unit of frequency is hertz. Unit of frequency is hertz. Hertz we will represent by capital letter H, small letter z. Hertz is actually equal to second to the power minus 1. Hertz is equal to second to the power minus 1. Note down. Can I erase? The next day, what is the connection, the relationship between frequency and wavelength? What is the connection between frequency and wavelength? So frequency and not wavelength. Frequency and what is the relationship between frequency and period? Frequency and time period. So what is the relationship between frequency and time period? We can write frequency that is equal to 1 over time period. Frequency equal to 1 divided by time period. That is why the unit of frequency is second to the power minus 1, because a unit of period is second. So unit of frequency is 1 by second. 1 by second is second to the power minus 1, and this is called hertz. And hertz we will represent by Hz. So we have done this also. This one, properties of periodic motion, that we have completed. Now I have given an example for periodic motion, that is motion of a spring. The oscillation of a spring is an example for periodic motion. For example, you can see here, when I hang this mass, so this is the original spring, correct? So this is the original spring, and this much is the length of the spring. So how much is the length of the spring? Just a minute, I will bring a ruler if I have one. So here we have a spring and this is my original spring. Yes, so what is the length of the spring? So length of this spring is about, where is 1 centimeter? Yes, here. So length of the spring is, for example, we'll start from here to this one. So it is about 5.5 centimeter. The length of the spring is 5.5 centimeter. Anyway, when I apply a force here, what happens? Its length increases, right? The length of the spring changes, means the size of the spring is changing and the shape of the spring also changes, right? Now the size and shape of the spring changed. Now the spring is oscillating. So during oscillating, what happens is the length of the spring is changing. So here you can see, if I remove this force, the spring will go back to its original shape. So when I applied the force, it changes its size. When I remove the force, it go back to the original shape, original size. When I applied the force, the size is changed. So this force, it changes the shape and size of the object, that is called deforming force. The force that changes the shape and size of the object is called deforming force. For this spring, what is deforming force? Deforming force, the force which changes the length of the spring. So I am just writing the definition of deforming force for this example. Particularly for this example, what is deforming force? The deforming force is force which changes the length. The force which changes the length of the spring. That is the deforming force. It changes the formation. It changes the force which changes the formation of the spring, right? So deforming, changing the formation, changing the size of the spring. Deforming, right? So changing the formation of the spring, that is the deforming force. So here, what is the deforming force? The deforming force is the weight of this mass added, right? Because the weight of the mass added, that force is changing the size of the spring. So when I remove this force, what happens is, when I remove this force, the spring go back to its original size, because spring is elastic, right? So there must be a force that is pulling back the spring to its original shape, correct? The spring regains its original shape. So what causes that regaining of the original shape? What helps the spring to go back to its original size? That force is called restoring force. When you apply a force here, that is the action, right? So there will be an opposing force acting on this weight. That opposing force is developed within the spring, and that will be directed towards the equilibrium position, and the restoring force will be opposite to the deforming force. So what is restoring force? Restoring force is the force that causes regaining the original size, that helps regaining the original shape. So now we will talk about the restoring force. Restoring force. So what is restoring force? Restoring force is the force that acts opposite to the deforming force. It helps to regain the original size. So I will write force helps to regain the original size of the spring. So we are writing this definition for this particular example. If you see another definition in the textbook in the internet, then don't get confused. I am writing this definition particularly for this example. So what is restoring force? Restoring force is the force helps to regain the original size of the spring. And restoring force, I will write restoring force like this, that will be always equal to deforming force, and it will be always opposite in direction, opposite in direction to deforming force, opposite in direction to deforming force. If deforming force is acting in the downward direction, if the deforming force is acting in the downward direction, then restoring force will be acting in the upward direction. We studied Newton's third law in the last year in grade 9, right? So Newton's third law states that force always act in pairs. Force cannot exist alone, cannot act alone. There will be always two forces acting. When this mass apply a downward force on the spring, then what is the reaction? The spring will apply an upward force on the mass. That upward force is the restoring force for this example. So what is deforming force? The force which changes the length of the spring in this example. And what is restoring force? The force that helps the spring to go back, the spring to go back to its original size. That is the restoring force. Now we will talk about the most important concept of this lesson, that is the simple harmonic motion. Simple harmonic motion. Is simple harmonic motion a periodic motion? Yes. Simple harmonic motion is a periodic motion. Is all periodic motion simple harmonic motion? No. All periodic motions are not simple harmonic motion. So now we are talking about simple harmonic motion. SHM, simple harmonic motion. So for example, in simple harmonic motion, so this is a spring, and if you apply a mass here, then the length of the spring will increase, right? So you are applying a deforming force, correct? You are applying a deforming force here. A deforming force, I will write D here. So there will be a restoring force acting in the spring, that will be in the opposite direction, right? This force is within the spring and it will be equal to the deforming force. So this is our restoring force, restoring force. Then if you apply more deforming force, means if you apply a greater deforming force, what happens? The length of the spring will increase, right? The length of the spring is increased, X. So here this is the deforming force, means now you are applying more deforming force, so restoring force will be also more greater, right? Greater than before. Restoring force will be also greater. If you apply more deforming force, then there will be more increase in length of the spring. So increase in length of the spring, that we will write displacement or distance. Displacement, for this textbook it is given distance. We say displacement or distance, or another name is extension. Extension, increase in length of the spring. So in your textbook they mentioned distance. So what happens is, when you apply more deforming force, there will be more increase in the length of the spring, correct? So when I apply a small force, increase in length of the spring will be small. If I increase the applied force, the length of the spring will increase more. So when you apply more deforming force, the increase in length of the spring will be more. Means the restoring force will be also more, right? So we can say in a simple harmonic motion, or in the case of the spring, restoring force is directly proportional to the increase in length of the spring. The restoring force is, I will write F, okay, because in the textbook it is written F. The restoring force is directly proportional to the increase in length of the spring. Do you understand? Why? Because means to increase the length of the spring more, you need to apply more force. So when you apply more force, there will be more restoring force. Restoring force will be always equal and opposite to the force you are applying to increase the length of the spring. So restoring force is directly proportional to the increase in length of the spring, that is distance, and restoring force will be opposite. F will be opposite to the direction of the increase in length of the spring, means direction of x or direction of the distance, opposite to x. So if any periodic motion satisfy these two conditions, any periodic motion obey these two conditions, then those periodic motions are called simple harmonic motion. So in a simple harmonic motion, the restoring force will be directly proportional to the distance, and it will be opposite in direction to the distance, means increase in length of the spring. For example, here you can see, what can you see? You can see a spring and a mass. So the length of the spring is little bit increased, and the restoring force will be acting upward direction, right? Because length is increased in the downward direction, so restoring force will be acting in the upward direction. Restoring force will be always act opposite to the direction of increase in length of the spring. Now I increase the applied force. So what happens? The length of the spring is increased more, so restoring force will increase more. Restoring force will be greater. Now again I am increasing the applied force. Restoring force will be again greater, because restoring force is directly proportional to increase in length, right? Now I increase in length of the spring like this, so restoring force will be more, again more. So, and it will be in the opposite direction. Increase in length of the spring is in the downward direction, and the direction of restoring force will be in the upward direction. So these are the two conditions for simple harmonic motion. One is restoring force acting within the spring, restoring force acting within the oscillating object, within the spring, that is directly proportional to the displacement, and the direction of restoring force will be opposite to the direction of the distance or direction of the increase in length of the spring. So if any oscillatory motion, any periodic motion satisfy these two conditions, are called simple harmonic motion. So I will just write the definition of simple harmonic motion. In a simple harmonic motion, you can write it down. In a simple harmonic motion, number one condition, restoring force. Restoring force. What is restoring force? The force which helps the spring to go back to its original shape, right? The restoring force is directly proportional. The restoring force is directly proportional to the distance. Here what is the meaning of distance? Here the distance means increase in length of the spring, right? Distance means increase in length of the spring. What is another name? Another name is extension. Okay. What is the next condition? The second condition. The second condition is, the second condition is what? The second condition is the direction of the restoring force will be opposite. Direction of restoring force is opposite. Opposite to what? Opposite to the direction of distance. Distance means increase in length of the spring, correct? Okay, so this is about the simple harmonic motion. Now we will go to the Hooke's law, and we have given examples for simple harmonic motion. Number one is oscillation of a spring and mass system. It can oscillate in the horizontal direction or it can oscillate in the vertical direction. For example, this oscillation of spring is simple harmonic motion, right? Simple harmonic motion. Oscillation of this spring is simple harmonic motion. And oscillation of a swing in the park, a child is moving like this. So this is an example for simple harmonic motion, because here the restoring force is directly proportional to the displacement from the equilibrium position. Then you can see here in the case of the swing is here. In the case of the swing, so it is the equilibrium position. At equilibrium position, restoring force will be equal to 0, because the displacement is 0. At equilibrium position, the displacement or the distance is 0 when the swing move like this. So when it is moving like this, you can see the distance or the displacement from the equilibrium position, EQ for equilibrium position. So the displacement is increasing. When displacement is increasing, what happens is when the spring is going like this, so the restoring force will be also increasing. If it is going like this, restoring force will be increasing. When it is going back like this, then restoring force will be decreasing. At equilibrium, restoring force becomes 0 when it will go to the other side, right? Other side. When it goes to the other side, displacement is increasing, right? Displacement is increasing, so restoring force will be increasing. And when it is going back like this, then restoring force will be decreasing. So here when it is going like this in this direction, this is the direction of the displacement, right? So displacement is along this direction, restoring force will be in the opposite direction. Here the restoring force, you can see the distance is along this direction, right? Then restoring force will be in the opposite direction. So you can see here restoring force will be always directed towards the equilibrium position. What? Restoring force will be always directed towards the equilibrium position, towards the equilibrium. I am not sure, are you able to see the bottom of the board? Equilibrium position. When displacement x is to this side, restoring force F will be in the opposite direction. So here when the displacement is to this side, x is to this side, force will be to the opposite direction. You can see when it is to this side, force is towards this direction. When the displacement is to the left side, force is to the right side. When displacement is to the right side, force is to the left side. Force will be always directed towards the equilibrium position. Restoring force will be always directed towards the equilibrium position. Note this point, this is very important. The direction of restoring force is always towards the equilibrium position. The next is Hooke's law. Hooke's law we will explain in the case of this example of a spring. What is Hooke's law? Hooke's law states that when you apply a force, the length of the spring will increase. When you apply more force, the length will increase more. What? When you apply more force, the length of the spring will increase more. That is the Hooke's law. Hooke's law states that if you apply more force, there will be more increase in length of the spring. And we have an equation in Hooke's law. The equation is F is equal to x, right? When you apply more force, there will be more restoring force. That restoring force is directly proportional to x. If there is more force applied, there is more increase in length. And we can write the force is equal to a constant into x. So this K is a proportionality constant. Whenever you replace the proportionality sign, this is the proportionality sign, whenever you replace the proportionality sign with an equal to sign, we have to multiply the equation with a constant. That constant here, it is K, and this constant is called spring constant. Spring constant. And in this equation you will see a negative sign here. This negative sign shows, or negative sign represent, this restoring force is always directed opposite to the distance, to the increase in length of the spring. So here in this equation, what is F? What is F in this equation? F is equal to restoring force. F represent restoring force. The magnitude of the restoring force will be always equal to the magnitude of the applied force, only the direction will be different. So F represent restoring force, and what does this X represent? X represent extension, which means the increase in length of the spring, or in the textbook it is given distance, so I will also write distance. So X is the distance, and what is K? K is spring constant. K is the spring constant. That is a constant for a spring. So we will explain what is spring constant. So in this equation, from this equation, what is K? If I just ignore the negative sign and write this equation, K is equal to F divided by X. Force divided by increase in length. So K, in simple term, I can tell for this spring the value of K is less, because this spring I can extend easily by applying a small force. I can stretch this spring, so it has a small value of spring constant, because by applying a small force I can stretch this spring. But there will be some spring now I do not have, that will be like very stiff, strong. We cannot stretch it, or it will be very stiff. It means that spring has high value of spring constant. So what is spring constant? Spring constant means how much difficult it is to stretch the spring. If it is very difficult to stretch the spring has high value of spring constant, and if it is very easy to stretch the spring has low value of spring constant. So spring constant K is equal to F divided by X. Remember this equation. What is K? K is equal to F divided by X. So from this equation, from the Hooke's law equation, we can see, that the force, applied force, okay, the force is directly proportional to the distance, right? The force is directly proportional to the distance. So here magnitude of the applied force will be always equal to magnitude of the restoring force. So only the negative sign, okay, the negative sign represents restoring force is opposite to the displacement. Okay, so here the force is directly proportional to displacement, which means if you increase the force, if you add more force, if you apply more force, the length of the spring will increase more, the distance will increase more. So here I will draw a graph of force against the applied force against the extension. The force against the extension, the force against the distance. Extension and distance, same thing. That's why I am telling both. So force against the extension, force in Newton against the extension in meter. Against the extension in meter. So here force and X are directly proportional if any two quantities are directly proportional. If one quantity is directly proportional to the other and you are plotting a graph between them, then the graph will be always a straight line. It will be always a straight line. If one quantity is directly proportional to the other and you plot a graph between them, then the graph will be always a straight line. So force distance graph for a spring will be a straight line. The force distance graph of a spring will be a straight line. So we can say spring obey Hooke's law. Spring obey Hooke's law. If any object's force against the distance graph is a straight line, then that object obey Hooke's law. The straight line graph represent the object obey Hooke's law. If you draw the force against the distance graph for a rubber, then the graph will not be a straight line, which represent rubber do not obey Hooke's law. Hooke's law means when you apply more force, there will be more extension, more increasing length of the spring. That force and increasing length of the spring are directly proportional. That is Hooke's law. Now you can see here, this is the graph. How to calculate the slope of this straight line graph? What is the slope of the graph? Slope is always equal to y divided by x, right? The quantity on the y-axis divided by quantity on the x-axis. So can you tell what is the quantity on the y-axis here? What quantity on y-axis? On y-axis here, this is the y-axis, right? And this is the x-axis. So on y-axis it is force. Force divided by, on x-axis what? X, right? Distance on the x-axis, f by x. So slope is equal to f divided by x. But you know that force divided by distance, that is equal to spring constant k, right? So slope, if you calculate the slope of this graph, you will get spring constant k. Spring constant what? Do you understand? Very difficult. Force distance graph, right? Force distance graph is a straight line. So if you calculate the slope of the graph, slope is equal to y2 minus y1 divided by x2 minus x1 means y by x, right? Quantity on y-axis divided by quantity on the x-axis. Quantity on y-axis is force, quantity on the x-axis is distance. So slope is equal to force by distance is equal to spring constant. So slope of force distance graph gives spring constant, correct? Slope of, write it down, slope of force distance graph is equal to what? Is equal to spring constant k of the spring, is equal to spring constant of the spring. Next is energy of a spring. So to stretch the spring, I am applying a force, means I am spending some of my energy to stretch the spring. Energy is conserved, right? Energy cannot be destroyed. So what happens to the energy I spent on the spring? The energy I spent on the spring will be stored as the potential energy of the spring. That potential energy stored inside a spring is called elastic potential energy. The potential energy stored within the spring is called elastic potential energy. What? I am spending, means when I stretch this spring, I am applying a force, which means I am spending some of my energy on the spring. Energy is conserved, energy cannot be destroyed. So energy changes one form to another, right? Energy changes from one form to another. So the energy I spend to stretch the spring will be stored within the spring as its potential energy. That potential energy stored in the spring is called elastic potential energy of the spring. It is called elastic potential energy. So there are two ways to calculate the elastic potential energy of the spring. One way is using the equation. Use the equation to calculate the potential energy of the spring. That equation is half kx squared. This is the equation to calculate the energy of a spring in that E is energy, 1 by 2 is 1 by 2, K is spring constant, and X is the distance or the increase in length of the spring, the extension. So X is the distance. So this is that equation to calculate the elastic potential energy of the spring. Then we have another way, one more way to calculate the elastic potential energy or calculate the potential energy of the spring, that is from the graph, from Hooke's law graph, from force extension graph or force distance graph. We can calculate the energy stored or elastic potential energy stored in a spring from the Hooke's law graph, that is the force distance graph. This area under this line, so this black color line, that is our graph, right? That is our graph line. So area under that line, area under this line will be equal to the potential energy. So if you calculate area under the graph, you will get the energy stored in the spring. Energy is equal to area under the line, right? Area under what line? The force distance graph. Area under force distance graph, that is equal to elastic potential energy of the spring. So this you can see the shape of this area, that is a triangle. So you can calculate area of the triangle by half multiplied the B means the base, right? The base of the triangle multiplied the height of the triangle. So half multiplied base multiplied height. So if you calculate like this, the area under the graph, the value, the calculated value will be equal to energy of the spring, the energy, the elastic potential energy stored in the spring. And students, if you like to participate, if you like to join in my online class, you can contact in the given number. And now we will go to the energy of oscillation or energy of an oscillating spring, oscillating pendulum, or a swing that is in oscillation, that is in motion. So energy of oscillation. So here is a swing, and this swing is oscillating like this. So it will go to this side, then it will go back like this, and to the other side, then it will again go back in the same path. So this is called one oscillation, right? This is called one oscillation. So we will talk about how the energy change take place in the swing, okay, when it oscillates. So here this is the equilibrium position, and this is the equilibrium position. So here it has the swing is moving like this, see here. So here it has the maximum displacement. The swing has maximum displacement here. So this is the maximum displacement, maximum X, maximum displacement. And we know that the potential energy, that is equal to half multiplied F multiplied X, right, where X is the distance. So here when the distance is maximum, the potential energy will be maximum. So at this position, potential energy will be maximum. Potential energy will be maximum. When potential energy is maximum, what will be the value of the kinetic energy? Its kinetic energy will be equal to 0. And the potential energy plus kinetic energy, that is called the total energy of the oscillation, total energy of oscillation. So potential energy of the swing will be maximum at a maximum displacement. So here the potential energy is maximum. When the potential energy maximum, the kinetic energy will be 0. So here when it is at a maximum displacement, this swing will be momentarily rest. It will be at rest for a short time. It will be at rest for short time. Now what happens from here? It starts moving, right? It starts moving back to the equilibrium. So when it is moving back to the equilibrium, what happens is when it is moving back to equilibrium. Okay, when moving back to equilibrium, then potential energy decreases. Potential energy will be decreasing and kinetic energy will be increasing. Do you understand? So at a maximum displacement of the oscillation, the potential energy will be maximum and kinetic energy will be 0. Then when it moves towards the equilibrium position, what happens is its potential energy will be decreasing. So the decrease in potential energy will change into the kinetic energy. So potential energy will be decreasing and kinetic energy of the oscillation, kinetic energy of the swing will be increasing, and the kinetic energy will be maximum at equilibrium. So at equilibrium, when it reach the mean position, when the swing reach here at the equilibrium, so then potential energy will be minimum. Its potential energy will be minimum and kinetic energy will be maximum. Potential energy become the lowest value and kinetic energy become maximum. So as kinetic energy here is maximum, means we know that kinetic energy is the energy of motion. When speed increases, kinetic energy increases. Kinetic energy will be maximum if speed is maximum, if velocity is maximum. So the oscillating object, the swing, will have maximum velocity at equilibrium position. The oscillating object will have maximum velocity at equilibrium position. So the swing will have its maximum velocity at its equilibrium position. Then what happens? It will go to the other side, right? Now it will go to the right side. When it goes to the right side, the displacement is increasing, right? When displacement increases, its potential energy will be increasing. Potential energy will be increasing. When potential energy is increasing, kinetic energy will be decreasing, and when it reach the maximum again here, the swing will be momentarily at rest, means the swing will stop there for a moment, then it will go back, right? So at a maximum displacement, potential energy will be maximum and kinetic energy will be equal to 0. So if I draw a bar diagram for the variation of change in kinetic energy and potential energy of this pendulum here, like we will draw here at this point, and here also we will draw the bar diagram, and at equilibrium also we will draw the bar diagram. So what I will do is I will erase these things here. So some part here, we need some space here, so I will erase here. Hope you can pause and take notes. So here at this point, yeah, here at maximum displacement, then we will draw at equilibrium, and we will draw this side also maximum displacement, and we will draw in between also, in between, okay, here in between the maximum and equilibrium, here also in between the maximum and equilibrium, we will draw the bar diagram or bar graph for the kinetic and potential energy of the swing. So here at maximum position, it has the maximum value of potential energy. So potential energy is maximum, and the kinetic energy, I will use blue color to represent kinetic energy. Here kinetic energy is 0. Then at equilibrium, its potential energy will be 0 and kinetic energy will be maximum, means all the potential energy converted to kinetic energy. Energy cannot be created, so it is changing from one form to another. Potential energy changing from the potential energy to kinetic energy, then kinetic energy to potential energy. So this energy change is happening. The form of energy is changing. Energy is not created. Then again at a maximum displacement here, the potential energy is maximum, correct, and kinetic energy is 0. Then in between the equilibrium and maximum displacement, the oscillating object will have potential energy and it will have kinetic energy also. So like this, in between the equilibrium and maximum displacement, the swing will have equal potential energy and kinetic energy if it is at the middle, if it is in between, at the middle of equilibrium position and maximum displacement. So this is a diagram, okay, a bar diagram. Here it is kinetic energy, this is kinetic energy, this blue color represent kinetic energy, kinetic energy, kinetic energy, kinetic energy here. So the black color represent potential energy, PE, PE, PE. Now we will talk about pendulum. We will talk about pendulum, a simple pendulum. A pendulum is a string, and at the one end of, means one end of the string is fixed here, it is fixed, and other end there is a mass. It is called a bob. So this will be oscillating. This pendulum will be oscillating. It's just like a swing. So the pendulum will be oscillating. So if it is oscillating slowly, that is an example for simple harmonic motion. So if the pendulum is oscillating like this, this is the maximum displacement on either side, right? So when it complete one full rotation, we call it is one cycle, right? Means one oscillation, we call it is one cycle of motion. So the time taken to complete one cycle is called time period. The time taken to complete one cycle is called time period. Time period we represent by the letter T, and the SI unit of time period is second, that you know. So what is the equation to calculate the time period of simple pendulum? The equation is T is equal to 2 pi into square root L divided by G. So the period of simple pendulum, period of a pendulum depends on the length of the pendulum and the acceleration due to gravity at that place. And what is the equation to calculate period? Period T is equal to 2 pi into square root L by G. Period is time. So this will be expressed, or this will be measured in unit. SI unit of time is second. So it will be measured in second, and this is what is given in your textbook about the pendulum. And there will be lots of questions to calculate the time period, to calculate frequency of the simple pendulum, and to calculate the length of the string, the value of the acceleration due to gravity at that place using simple pendulum. All these numericals I have solved in another video that you can watch. To solve means to know how to solve all the questions in this chapter, you can watch the other video I have uploaded in the YouTube in my channel. So next is resonance. The last concept is resonance. Number 9, resonance. Talk means I will explain resonance in two different ways. Number 1, so what is resonance? Resonance means equal frequency. Resonance means equal frequency. That is frequency of one object, frequency of one object that become equal to frequency of other. I will explain this clearly. The frequency of one object, what is this one object? That is a vibrating object or an oscillating object, an object that is in motion, that is in vibration. So frequency of object vibrating, or frequency of vibrating object, this object is in vibration. The frequency of vibrating object become equal to frequency of, become equal to the natural frequency, become equal to natural frequency of any other object, natural frequency of other object. So they are in contact, okay, natural frequency of other object. What happens is maximum energy will be transferred from this object to the other. Maximum energy will be transferred from this vibrating object to the other. This is called frequency. Sorry, this is called resonance. So here we have one object here. This is one object. This object is vibrating. Okay, this object is vibrating. And we have another object that is in touch with the vibrating object. Here we have another object. that is in touch with the vibrating object. Okay, this other object is in contact with the vibrating object, and if the frequency of this vibrating object or the frequency of vibration, if this frequency of this vibration become equal to natural frequency of this object, then maximum energy will be transferred from this vibrating object to the other object, and that object will start vibrating faster, start vibrating with a greater amplitude. That situation is called resonance. I will explain again. So we have a car here. Yes, this is a car. Yeah. Okay, car, and this is the tire of the car. Okay, only one tire I am drawing. Yeah, one more. Okay, so this is the car tire. So here what happens is this car is rotating. This car is means the car is not rotating, the tire is rotating. The tire is rotating, so it will have a frequency, right, with number of rotations completed in 1 second. So if the rotational frequency of the tire become equal to the natural frequency of the car, then maximum energy will be transferred from the tire to the car. That is called resonance. So there is a question, what is the meaning of natural frequency? Natural frequency means every object will have its own frequency. That frequency is called natural frequency or resonant frequency. That is the property of the object. For example, my body will have a natural frequency. This table will have a value, its own value of natural frequency. So every object here, every object everywhere will have its own value of natural frequency. So natural frequency of an object depends on its mass, depends on its size, and natural frequency of an object depends on its shape. For example, the natural frequency of this car is 100 Hz. Just giving example, okay, the natural frequency of the car is 100 Hz, and if the tire is rotating at a frequency of 100 Hz, then maximum energy will be transferred from the tire to the car, so the car will vibrate faster, the car will shake faster. And if the rotational frequency of the car means the car is making only 80 rotation in 1 second, so now only making 80 rotation in 1 second, so frequency is 80 Hz. Then you can see the frequency of rotation of the tire is not equal to natural frequency of the car, so only means maximum energy will not be transferred from tire to the car, only some energy or little energy will be transferred from tire to the car. So this time the car will not vibrate faster, it will not shake that much. So here if the car is increasing its speed and the tire is making 120 rotations in 1 second, so the frequency of rotation of the tire is 120 Hz, then now also the frequency of rotation of the tire is not equal to the natural frequency of the car. So maximum energy will not be transferred, only little energy will be transferred from tire to the car. So resonance will not happen. Resonance happens when the frequency of vibration or frequency of rotation of an object become equal to the natural frequency of the other object that is in contact with it. So maximum energy will be transferred from the vibrating object to the other object. That condition, that situation is called resonance. So this is one explanation or one way of explanation of resonance from my side. And I will give you one more example here. That is like we have a washing machine here. So what does this washing machine do? So in that washing machine here, So we have a dryer here, dryer what, dryer or spinner something. So this dryer, okay, so it will be rotating, right? So this is the dryer. So this will be rotating, spinning like this, right? Spinning. If its frequency of rotation, become equal to what? The natural frequency of the machine. If the frequency of rotation of this drum, of this dryer, become equal to the natural frequency of the machine, then maximum energy will be transferred from the dryer to the machine, and the machine will vibrate faster, the machine will shake faster. So it will shake and it will move. The machine here does that. Then if, for example, the natural frequency of this machine is I will say 50 Hertz is the natural frequency of the machine. So this natural frequency depends on what, or how does it have a natural frequency? That is its own property. Every object will have its own value of natural frequency. That depends on the mass of the object, size of the object, and shape of the object. So now this washing machine, its natural frequency is 50 Hertz, and if this dryer is rotating with a frequency of 30 Hertz, the frequency of 30 Hertz, then the rotational frequency is not equal to the natural frequency of the machine. This I will make a small change here, okay? I will make a small change here. I will make like this. This is rotating at a frequency of 60 Hertz. 60 Hertz. So 60 Hertz is the rotational frequency of the dryer. That is not equal to the natural frequency of the machine. So maximum energy will not be transferred, only little energy will be transferred. So machine will be vibrating with a little amplitude, not much big vibration, little small vibration. Then if we if I pour some, means if I fill some water, or if I add some cloth in this washing area, so what happens is its mass changes, right? When mass changes, its value of natural frequency changes. For example, now its natural frequency is 60 Hertz. How natural frequency change it? The natural frequency change it because we changed the mass. How mass change it? By adding cloth or by adding water into the machine. Now the natural frequency become equal to the rotational frequency of the dryer. So what happens is maximum energy will be transferred from the dryer to the machine, and the machine will start vibrating faster, machine will start shaking faster with a greater amplitude. So it will shake and it will move. Then next, yes, another way I want to explain resonance is, that is given in your textbook, that is resonance occurs when forces are added to a vibrating or oscillating object at a time interval that is equal to period of oscillation. Resonance occurs when forces are added to a vibrating object. When forces are added to a vibrating or oscillating object, you will understand the difference later of vibration and oscillation. Vibration means it is vibrating, so amplitude will be small, displacement will be small. Oscillation means moving in periodic motion with a greater displacement or greater amplitude. Oscillating object at a time interval, at a time equal to period of oscillation, equal to what? Equal to period of oscillation. Period of oscillation. So what is resonance? Resonance occurs when forces are added to a vibrating or oscillating object at a time interval that is equal to period of oscillation. Do you understand? I can make you understand by giving a very simple example. So in the park, I am in the park with my small son. So he is using swing. Then what? I am pushing the swing. It will go, come back. So the time taken to complete one oscillation, time taken means time taken to go and come back, that is called one time period, right? Then again I am applying the force, it's going, coming back, applying the force, going, coming back, applying the force, going, coming back. So I am applying force on the swing, I am applying force on the swing at a time interval that is equal to period of oscillation, right? That is equal to period of oscillation. Do you understand? I am applying the force, then it's going, the swing is going, coming back. After that time I am applying the next force. So the time between I apply the force, the first force and the second force, I apply the time interval. The time between that two forces is equal to the time period of the oscillation. So what happens is energy will be added. Each time energy will be added to the swing, and the swing will start oscillating faster, right, with a greater amplitude. So it will continue until he fly off the swing. Then the same example is in the trampoline. So this I did not experience, the other one, the swing case we experience usually. So in the swing case, if the man is jumping, means in the trampoline, okay, if the man is jumping onto the trampoline, a force is applied, right? A force is applied onto the man by that elastic sheet. So he will go up, then go down, again force is applied. So his energy increased, right? When a force is applied, energy will increase. He will go higher, then again down, again energy is up, means force is applied. So here force is applied after equal time interval that is equal to period of oscillation, and each time the energy will be added to the oscillating system and its amplitude of oscillation continuously increases. So in the case of swing, why we do not experience, or the small boy don't experience the greater amplitude is each time it's not increasing, right, or it is oscillating with the same displacement, that because there will be air resistance, right? So it is called damping. Because of air resistance, some of the energy will be lost to the air, some of the energy of the swing will be lost. So to balance that, I was applying the force. If there was no damping, no friction, so each time when I apply the force, what happens? Energy will be added to the swing, and the swing will be oscillating with a greater amplitude, and if we continue that, it will be much greater. And so this is all about the lesson 1, periodic motion, in the chapter 1, vibrations and waves. And I have made another video to solve all the questions, all the numerical problems in the textbook. And once again, students, if you want to join, if you like to join my online class, you can contact in the given number. Thank you for watching. Good luck.